Hi, how are you? My name is Augusto Cesar. The title of presentation is a strategy to obtain initial distributions of points adapted to the problem when using the generalized finite difference method. Here, a brief scheme of our presentation. First, I will introduce the origins of the method and the objective of the presentation. Later, theoretical aspects of the method, the strategy, applications, and finally the conclusion. The contributions of Liska and Orkis were particularly important in advancing the method, as they used started with 8 points in the movie where the least squares process to minimize errors. Later, Benito analyzed the impact of different factors in the stars concerning the accuracy of the derivatives using the second order approximation. I want you to make it clear that we are not proposing an adaptive strategy. We propose a strategy to obtain discretizations adapted to the problem. The strategy consists of using a coarse initial discretization for the calculation of gradients. Later, we get an adapted discretization based on these gradients. You consider the boundary value problem. In the first line, we have the differential equation, and in second, we have the boundary condition. Let me talk a bit about the theoretical aspects of the method. For each point xi, we consider the Taylor expansion centered at x0. We consider the Taylor series up to fourth order terms. The series truncations leads to a residual as shown here. P is the coefficient matrix where the number of lines depends on the number of points per stars. Du is derivative matrix and delta U is vector of the unknown values. After applying the residual minimization process on the Taylor series, we can obtain the derivative matrix. The matrix explicit form is shown here, where the coefficients are obtained in the calculation of the matrix A. The process is ended when we substitute the derivative matrix in the differential equation. This is made to each point of the domain. We are using a fourth order approximation. Thus, for better accuracy, a greater number of points on the stars are required when compared to the second order approximation. Due to the frequent singularities associated with the higher numbers of points per stars, we use a strategy based on the condition number to detect the reconditioned stars, and thus be able to treat on these stars, changing the formation criterion and increase the number of points stars. The strategy is carried out in 3 stages. We get a first approximating with an initial curse distribution of points with second order approximation. See the image on the left. Then we compute the gradient using the operators in GFDM. Finally, we obtain an adapted distribution considering the high gradient regions of the problems using fourth order approximation. Now, let me tell you how we obtain an adapted distribution. Each point has influence regions with length delta. The points are divided inside these regions as shown on the right. The region can have 9 points. This depends on the gradient. For instance, one point with gradient higher than the average plus 1.5 of standard deviation will receive 9 points. We do not calculate the gradient in the boundary points. After the gradient calculation of the internal points, each internal point has an associated gradient. Each boundary point searches the closest internal point and divides itself according to the corresponding gradients of the search internal points. Application. In second order approximation, as user starts with 8 points, we use a potential weighting function with support 4, and the global arrow is shown here. To the case 1, we go to consider a rectangular domain with a singularity at point 0, 0. Here, we show the result of 4 discretization, the uniform initial to uniform, and the adapted. The initial discretization on is used to obtain the gradients. In this case, the accuracy is not important. The 2 uniforms were chosen with the objective to answer the question: where is the precision of the adapted discretization compared to uniform discretization? We can observe that the adapted discretization has a similar accuracy in relation to the uniform discretization with 625 points. Approximately 24% of the number of points in the reference uniform distribution has used in the adapted discretization to obtain a similar precision. To the case 2, we consider a rectangular domain. The image on the right is just to show where are largest gradients on the sides. A specific side has a higher gradient than the other sides. Approximately 42% of the numbers of points in the reference uniform distribution was used in the adapted discretization to obtain a similar precision to uniform 2. To the case 3, we will consider a cycle domain with a higher gradient at point 0, 0. The image on the higher is just to show where are the largest gradients. Here we can see that the adapted solution with 176 points has an accuracy between 1,719 and 1,789 points of the uniform discretization. Note the adapted discretization here in the cycle. Approximately 51% of the number of points in the reference uniform distribution was used in the adapted discretization to obtain a similar precision to uniform 2. In this case 3, we have a relatively higher number of points. We show here the advantage of the strategy in terms of computational cost. Comparing the adapted discretization with the uniform 2, we have a speed up of about 2. Conclusions. Instead of using a general discretization, we are proposing an adapted discretization. The strategy is based on the prior computation of gradients in a cross discretization. We have shown that with the adapted strategy, we achieve similar accuracy with a much smaller number of points in a shorter runtime compared to uniform discretization. Thanks. Questions?